In this video, we will give a conceptual reason for why the second derivative test is true. So I want to motivate this by recalling a second derivative test for one variable functions. So for one variable functions, f of x, if c is a critical number of f. So remember, a critical number of f is a value such that the derivative at c equals 0, or the derivative at c is undefined. So if that's the case, if c is a critical number of f, and the second derivative of f at c is greater than 0, then f has a... So before I say what it has, I'm going to motivate this with a picture. So I'm going to draw my axes. And let's think about what this statement means. The second derivative is positive. That means f is concave up. Second derivative being positive means concave up at c. So let's say that c is here, and I need to draw a function that is going to be concave up at that point. So concave up is something like this. It's sort of like a upwards parabola type shape. Okay, so it's concave up at c, and I know that c is a point where my graph gets flat like this because it's a critical number. And I can see based off of the graph that f has a local min. F has a local min at c. So this is part of what the second derivative test for one variable function says. I have a critical number, and my second derivative at that critical number is positive, then it gives me this concave up shape, which would give me a local min at that critical number. So I could say something similar when my second derivative is negative. The picture this time, let's say this is where c is. If the second derivative is negative, now that's going to mean that f is concave down at c. So that's going to have a shape like this. It's got to be concave down at this critical number. And I can see that that corresponds to a local max. So f has a local max at c. Awesome. Okay, so there's one more possibility, which is what if the second derivative at that critical number is 0? Then it turns out that this test, the second derivative test, is inconclusive. So by inconclusive, I mean that there could be a local max, a local min, or neither. You could also have a situation where that critical number is not a max and is not a local min. So as an example, to see why this is the case, let's look at two functions. Let's say that f of x is x cubed, and let's say that g of x is x to the fourth. So I'm going to take derivatives and second derivatives of each of these. So for f, the derivative is 3x squared, and the second derivative would be 6x. If I do the same thing for g, its derivative is 4x cubed, and its second derivative is 12x squared. All right, so I can find the critical numbers by taking these derivatives and setting them equal to 0. So if I did that for f and its derivative, we'd see that my critical point occurs when x equals 0. And it also turns out the same thing happens for the function g. Its derivative also is going to be 0 when x is 0. Okay, so now let's see what we get if we plug that critical point into the second derivatives. So if I plug in the critical point 0 into the second derivative of f, I'll get 6 times 0, which is 0. If we do the same thing with g, and I plug the critical point into the second derivative of g, we'll get 12 times 0 squared. Well, that's just going to be 0 as well. Okay, so both of these are situations where my critical point, when I take it and plug it into my second derivatives, I am getting 0. So now I'm going to draw the graphs of the original functions to show that in f and g, different things happen. And that's why it's going to be inconclusive. So what does the graph of x cubed look like? Well, x cubed is the graph that sort of snakes upwards. It's momentarily flat at the origin, and then it continues snaking on up like this. The graph of y equals x to the fourth is really similar to the graph of y equals x squared. It's just a bit narrower, because the y values get bigger a whole lot more quickly than they do in x squared. But looking at these two graphs, I can see that in the x cubed graph, where this critical point happens, this is neither a max nor a min. But in the other graph of x to the fourth, where that critical point is, that is definitely a local min. It's a low point. It's the bottom of a valley here. So from just knowing that the second derivatives of these functions were 0 at the critical point, I wasn't able to determine conclusively, like, was it a local max or a local min, or even neither. It turns out either one of those things can happen. So that's why the test is inconclusive. Okay, so that was a bit of calculus review. But there's something similar that we can say for two variable functions. So let f of x comma y be a two variable function. And we've seen that the second derivative test involves this term h, the Hessian, which is fxx times fyy minus f of xy squared. And what I want to notice about this initially is that this term, the f of xy squared term, that must be, because I'm squaring it, greater than or equal to 0. It can't be negative after you square that real number. So if I think about our first case of the second derivative test, that was, well, what does it mean if h, our Hessian, is greater than 0, if it's positive? Well, if this whole thing, I'm just going to highlight it, if this whole thing is positive, and I know that fxy squared is greater than or equal to 0, that forces fxx times fyy, that must also be a positive number. That must also be positive. Because if it was negative, you'd get a negative number minus this positive value, which would end up being negative. Okay, so fxx times fyy has to be positive. And if you multiply two numbers, and that's positive, this implies that fxx and fyy have the same signs. Either they're both positive or they're both negative. So that gives us two cases. So I'm going to call the first case, case 1a. So in case 1a, let's suppose that fxx is greater than 0. And if that's greater than 0, we already know in this case, in situation 1, that both of these terms are going to have the same signs. So that also means fyy would have to be greater than 0. So if I draw a graph, a 3D axes, so my z-axis, my x-axis, my y-axis, let's go in the negative directions. So negative z, negative y, and negative x. What do these second derivative things tell us about concavity? Well, fxx being positive means that our function, whatever our surface looks like, it's concave up if you just look at it in the x direction. And the fact that fyy is positive means it's also concave up if you look at it in the y direction. So it's concave up in the x and y directions. Okay, so I'm going to draw a picture of a surface where something like that happens, and then talk about, well, what does it mean for it to be concave up in the x direction? What does it mean for it to be concave up in the y direction? So a surface where that happens is if I have something like a parabolic bowl. So let's make it look like a bowl. So there's a cross section. Maybe a cross section has this circular or ellipse type shape. Okay, but I have a parabolic bowl like this. So if I were to slice this thing in the y direction, that slice would look something like, so it would slice it at this left end, and then all the way towards the right end. That's a slice in this y direction. A slice in the y direction. And notice that that curve that it slices out, that intersection curve, is definitely concave up. So now if I slice this in the x direction, I would end up getting, something at the front of this bowl. The front would be somewhere here. And then it would take it down to the bottom of the bowl, and then towards the back. So the back I can't see, so I draw with a dashed line. Okay, and that is a slice in the x direction. And I really got to put my 3D hat on and try to visualize this the best I can when it comes to drawing these things like slices. But if I look at this slice in this x direction, notice that that is also concave up. Okay. So the fact that it is concave up in both of those directions makes that point, this bottom point, it makes this a local min. And that's what the second derivative test says. In this case, when the Hessian is positive and fxx is positive, there is a local min. We've actually given a conceptual reason for why that's the case. Okay. So it could also happen that fxx was less than 0. And if it was less than 0, well, then fyy would have to have the same sign in this situation 1. Okay, so I'm not going to work this one out. I'm just going to say that this one is similar. It's quite similar to case 1a. And there's two other scenarios. There's situation 2 and situation 3. In situation 2, we said, what if our Hessian was less than 0? In situation 3, we said, well, what if the Hessian is equal to 0? These are harder to show. Okay, so I think it's helpful to see this picture because it's helpful to have this conceptual, knowledge of where does this come from? Like, where does this second derivative test come from? Why does it tell me I have a local min, for example, in this picture that I drew? It helps make it so that there's a little bit less memorization involved. And having this visual picture can really help reinforce our understanding of the test. So in terms of our goals for this section, in the last few videos, we've talked about the second derivative test and worked out a few examples to apply it to find local mins and maxes of multivariable functions. In the next set of videos, we are going to focus on doing applications of this to scenarios involving revenue, cost, and profit, and supply and demand.